In the years leading up to World War II, America's engineers worked in quiet corners of workshops and naval laboratories, rarely recognized, seldom praised, yet their minds built the foundation on which the nation's might would stand. Among them was a man whose name would never appear in front-page headlines or grand ceremonies, but whose invention, simple, cheap, and almost overlooked, would redefine naval warfare. He was not a general or an admiral, not a man of politics or influence, but an engineer who believed that the answer to the Navy's greatest problem could be solved not by billions of dollars, but by a few ingenious dollars well spent. His creation cost less than 20. Yet it would become one of the most reliable, deadly, and transformative weapons the United States had ever built. It would turn fragile floating runways into fearsome strike platforms. It would double the reach and confidence of American carriers across the vast Pacific. It would turn desperation into dominance. In the early 1940s, America's aircraft carriers faced a growing crisis. The Navy had invested enormous resources into these mobile airfields, betting on the idea that air power at sea would decide the war. But the planes aboard them, especially the new dive bombers and torpedo aircraft, were fragile machines, filled with experimental systems, complicated hydraulics, and delicate weapon mounts that often failed under pressure. When a plane missed its target or jammed mid-run, a pilot's chance of returning alive dropped sharply. Maintenance crews on deck struggled to keep weapons aligned, sights calibrated, and guns functional in the salty chaos of the open sea. Reliability was the missing ingredient. A gun that failed once in 10 battles could cost a fleet its air cover. The Navy needed something light, foolproof, and unshakably reliable. That was when the engineer entered the story. His name, rarely mentioned outside technical archives, was George Hyde, a craftsman of mechanical simplicity. Working in the shadow of more famous designers, Hyde believed in one principle: a weapon should never ask the user to think. It should work when wet, when frozen, when dropped, when dirty, and when forgotten. Hyde's design philosophy came from the battlefield reports of the Great War, where guns clogged with mud and jammed under stress. He studied failures not as shame but as teachers. He sketched out mechanisms so simple that they looked primitive, yet they never quit. His mind was wired to reduce, to strip away, to find truth through simplicity. In a world of over-engineered complexity, Hyde's $20 weapon was a quiet revolution. His concept began not for aircraft, but for defense. A compact submachine gun that ground crews and pilots could use to protect themselves if shot down or attacked on deck. It was meant to be cheap, mass-producible, and immune to precision requirements that slowed other weapons production. The Navy dismissed it at first. It looked too crude. But when test units were shipped to carrier decks in 1942, something remarkable happened. The weapon, unassuming, built from stamped steel with few moving parts, performed flawlessly. It did not jam. It did not rust. It did not overheat. Pilots carried it into the water after crash landings, pulled it out covered in salt and sand, and it still fired. Word spread quickly through the decks of the USS Enterprise, Yorktown, and Hornet. Sailors called it the gun that doesn't care. The official name would later be standardized, but among crews, it became simply the $20 miracle. Its low cost allowed thousands to be produced, distributed, and maintained without fear of waste. Its operation was so intuitive that even a mechanic with no training could use it effectively. Hyde's design solved not just the problem of combat reliability, it solved the problem of logistics. It was a weapon that asked for nothing and gave everything. And as carrier warfare evolved, this humble invention began to shift the balance of power. By 1943, the Pacific had become a chessboard of attrition. Japan's Zero fighters, skilled pilots, and hardened fleet made every American advance costly. The U.S. Navy needed not only better aircraft but a fighting system that could endure without faltering. Carrier decks became ecosystems of chaos. Aviation fuel, munitions, and heat mixed with mechanical stress and human exhaustion. Amid this madness, the small $20 gun became a symbol of reliability. Crews used it to defend against deck raids, to protect engineers during refueling, and even as emergency tools in desperate fights. The gun's dependability meant one less uncertainty in a sea of danger. Reports from the Navy Bureau of Ordnance began noting that maintenance time per weapon dropped by over 70% when using Hyde's model compared to earlier systems. While other guns needed precise cleaning and calibration, his weapon could be stripped, cleaned, and reassembled in under 2 minutes. The manual for it was a single sheet of paper. For a Navy constantly moving, constantly fighting, constantly repairing, that simplicity was priceless. Each minute saved on maintenance meant another plane launched, another sortie flown, another life spared. Behind the scenes, the War Production Board and the Office of Naval Research began studying the deeper implications. Could Hyde's method, low-cost precision through simplification, be applied to larger weapon systems? The idea fascinated Navy engineers. What if carrier-mounted guns, flak systems, or even torpedo launch controls followed the same principle? What if complexity was the enemy of reliability? What if victory at sea was not about more money, but about smarter design? These questions began reshaping the Navy's engineering doctrine. Technical bulletins from 1943 and 1944, now declassified, show a marked shift toward modular design, quick assembly, and field-reparable systems. The influence of Hyde's $20 gun rippled far beyond its original purpose. It inspired rethinking of everything from bomb release mechanisms to hydraulic systems that controlled aircraft elevators on carriers. The result? Fewer breakdowns, faster deployment, and ultimately, a doubling of the Navy's effective strike rate. By late 1944, American carriers could launch twice as many sorties in the same window of time compared to 1942. Officially, this improvement was credited to advancements in logistics and crew efficiency. Unofficially, many historians and Navy engineers later traced part of that leap to a cultural transformation, a belief, born from one engineer's $20 miracle, that reliability was the greatest force multiplier of all. When the war turned at Midway and later at Leyte Gulf, it was not just superior strategy or bravery that won the day, it was trust in the tools. The pilots who took off in darkness, the mechanics who rearmed planes between waves, the gunners who stood exposed on deck. They all relied on the certainty that their weapons would work when the moment came. That certainty in war is everything. The difference between a functioning gun and a jammed one is not just metal, it is life, momentum, and morale. Hyde himself never sought recognition. He worked quietly at Inland Manufacturing, later absorbed into the General Motors division, producing arms and mechanisms that followed his original vision. He was an engineer's engineer, a man who saw perfection not in elegance but in endurance. To him, beauty was in a machine that never failed. When interviewed briefly by a Navy historian after the war, Hyde said only, "I just wanted something that worked every time." That was his epitaph in spirit. What he built worked not just every time, it worked for everyone. From pilots clinging to life rafts to Marines defending island perimeters, Hyde's design became a silent partner of victory. It embodied the American idea that ingenuity could outmatch extravagance. It showed that the true measure of innovation was not cost or complexity, but consistency under fire. And as victory approached and the war's thunder began to fade, the lesson endured. The might of a nation rested not on grand machines alone, but on the small miracles that never broke, never jammed, and never quit. By 1944, the United States Navy had learned a lesson that no textbook could teach and no admiral could predict. Reliability wins wars. What began as an engineer's experiment on a workbench had evolved into a philosophy that reshaped the most powerful fleet ever to sail. Hyde's $20 gun was no longer just a weapon. It was a symbol of what American ingenuity could accomplish when stripped of pride and guided by practicality. The Navy adopted his principles in every corner of the fleet, from the smallest components of flight deck machinery to the massive operations controlling squadrons that launched at dawn and landed at dusk. Every system that mattered was redesigned to survive failure. Hydraulic lines on elevators were made modular. Gun mounts were simplified so that even a sailor with no formal training could replace a part in minutes. Electrical systems on carriers were compartmentalized, following Hyde's logic of isolation. If one circuit failed, the others must not die with it. A philosophy born from one man's workshop began spreading through every shipyard from Norfolk to San Diego. The Pacific War demanded such thinking. Japan's forces fought with incredible precision and courage, but their equipment, while often elegant, was fragile. Reports from captured airframes and wrecked ships revealed delicate engineering prone to failure under field stress. American engineers, guided now by wartime urgency, turned this difference into an advantage. Where the Japanese Zero demanded fine-tuned maintenance, the new American weapons demanded none. Where the enemy's guns required custom machining, Hyde's influence demanded that everything fit anywhere, anytime, with any hand capable of tightening a bolt. By mid-1944, the Navy's carriers had evolved into floating fortresses of repetition and trust. Every sailor knew his tool would work. That certainty, multiplied across tens of thousands of men, became something greater than hardware. It became confidence, rhythm, and speed. Deck crews rearmed aircraft faster. Ordnance handlers worked under fire without hesitation. Pilots, knowing their guns would never jam, attacked lower, risked more, and struck harder. The fleet moved like a single living organism, pulsing with mechanical harmony. War correspondents aboard the USS Lexington and USS Bunker Hill wrote of the strange calm that defined American flight decks during combat. Men who once panicked under air raids now worked with machine-like composure. The tools never failed them, and so they learned not to fail each other. Out of that synergy rose the doctrine that would double carrier strike power: constant readiness. Before Hyde's influence, carrier warfare followed a rigid rhythm. Sorties launched, decks cleared, maintenance performed, and then another wave hours later. But as equipment reliability grew, the pauses vanished. The Navy realized that with dependable systems and rapid repair, carriers could maintain almost continuous air operations. In the span of a single day, a task force could deliver 2 to 3 times the tonnage of bombs compared to 1942. This shift wasn't just statistics, it was transformation. The Navy Bureau of Aeronautics documented this evolution in late 1944. Operational reliability of ordnance and flight systems now permits sustained offensive output, surpassing prior projections by 100%. That single sentence, buried in an internal report, marked the moment America became unstoppable at sea. The Japanese fleet, once dominant, began to crumble not merely from lack of fuel or pilots, but from exhaustion, outpaced, outlasted, and out-engineered. In the Battle of the Philippine Sea, known later as the Great Marianas Turkey Shoot, American carrier aircraft decimated Japanese forces with stunning efficiency. Over 600 enemy planes were destroyed while American losses were minimal. What history books later summarized in numbers was in reality a triumph of endurance. Guns did not jam. Bomb racks released without error. Communication lines stayed alive even under strafing. That was Hyde's legacy in motion, the invisible reliability woven into every trigger pull, every system click, every engine start. After the battle, Admiral Raymond Spruance reportedly remarked in private that the Navy's true victory lay, not only in courage but in the machines that refused to fail. He did not name Hyde, and perhaps he never knew his name, but he had witnessed the ripple of his work. Inland manufacturing, where Hyde had begun his design, became a vital node in the war industry. Its production lines churned out tens of thousands of the $20 guns, each tested, inspected, and stamped with serials that traveled across the globe. The U.S. Marine Corps used them on island assaults. Pilots kept them in survival kits. Even British sailors, through Lend-Lease, carried them aboard Arctic convoys. Everywhere they went, the reaction was the same: they worked always. It is difficult, decades later, to imagine the psychological power of such trust. Soldiers and sailors lived surrounded by uncertainty. A storm could sink a fleet. A single mistake could kill hundreds. Yet in their hands was a small machine that never betrayed them. That trust in steel became trust in mission. It was a morale weapon as much as a physical one. When the Navy analyzed post-war combat data, it found that carrier sortie completion rates had doubled between 1942 and 1945. Maintenance downtime had been cut in half. Supply demands for replacement guns dropped to record lows. These numbers told a story of evolution, but behind them lay the human truth: an engineer's refusal to accept that complexity should define greatness. Hyde's design proved that greatness was consistency, that the perfect weapon was not the one with the most features, but the one that never failed to fire. As the Pacific Campaign advanced toward the Philippines, Iwo Jima, and Okinawa, this principle became doctrine. Commanders began demanding Hyde-standard systems, equipment that could be built fast, repaired faster, and never quit. Navy blueprints from 1945 show a remarkable pattern: simplified schematics, modular components, instructions written for sailors instead of scientists. The entire design language of war had changed. The Navy had gone from dependent to adaptive, from reactive to proactive. And so, while battles raged in distant waters, another silent battle was being won in drafting rooms and factories. Engineers who once idolized precision above all now sought resilience. They tested equipment in salt spray, mud, and fire, and expected it to survive. They called this the Hyde test, a tribute to the man whose weapon had set the standard. To pass the Hyde test meant a machine was not fragile, not fussy, but fit for war. At the National Archives, one report written after Okinawa sums it up. Combat efficiency is no longer the art of complexity, but the science of certainty. That line, understated and bureaucratic, captured the spirit of an entire generation of wartime engineers. They had learned that a $20 gun could change the rhythm of the Pacific, not because it was powerful but because it never quit. When the Japanese Empire finally surrendered in August 1945, the celebrations filled streets, ships, and skies. Fireworks roared, bells rang, and sailors hugged strangers on foreign docks. Yet in machine shops and shipyards, a quieter pride settled in. The men who built the tools of victory, the welders, machinists, and engineers, knew they had changed history not through grand gestures, but through invisible perfection. Hyde's $20 gun was retired from production after the war, but its DNA lived on. In post-war years, when the U.S. military began developing new automatic weapons and naval systems, engineers kept referring back to its schematics. Simplicity, reliability, affordability, these became pillars of Cold War design. In a strange way, a single low-cost invention had written the blueprint for the superpower age. George Hyde returned to a quieter life, his work buried in archives and factory records. Yet every carrier that sailed afterward, every weapon designed for endurance, carried his fingerprints. And as America transitioned from wartime to peace, from desperation to dominance, it was his philosophy that ensured the engines of defense would keep turning. He had proven something fundamental, that the strength of a nation lies not in what it spends, but in what it builds to last. When peace finally returned, the factories fell silent. Assembly lines that had once thundered day and night now stood in uneasy quiet, echoing with the memory of war's urgency. Yet inside the Navy's design bureaus and research divisions, a new kind of war was beginning, a war of ideas. What had been proven in combat was now being studied in theory. Reports flooded Washington from across the Pacific, documenting a simple truth that bureaucrats could no longer ignore. The nation's decisive victories were built not on luxury, but on reliability. The phrase Hyde Standard began to appear in internal memoranda and procurement guidelines, not as a formal doctrine but as a mindset, a quiet revolution in how America would build its weapons, machines, and even its identity. Inland manufacturing's wartime design was dissected line by engineers from the Naval Research Laboratory, Aberdeen Proving Ground, and Springfield Armory. They marveled not at what it contained, but at what it omitted. Every missing spring, every reduced machining step, every flat angle of stamped steel told a story of deliberate restraint. George Hyde had accomplished something most engineers struggled against their entire lives. He had made something perfect by removing everything unnecessary. This minimalist brilliance now became the foundation for post-war defense philosophy. The Navy Bureau of Ordnance published a classified technical digest in 1946 titled Economy of Function in Combat Arms. Within its pages, Hyde's work was cited repeatedly as a paragon of sustainable simplicity. That phrase, tucked among graphs and schematics, defined a generation of Cold War engineers. America's new challenge was not merely to build better than its enemies, it was to build smarter, faster, and with systems that could survive neglect, disrepair, or even catastrophe. The world was changing. The nuclear age had begun, carriers were evolving into jet-powered platforms, and the idea of constant readiness was no longer wartime necessity but peacetime policy. The same principle that made a $20 gun invincible in the Pacific now guided the construction of entire fleets. The first post-war Essex-class refits integrated modular electronic bays that could be replaced at sea without dry docking. Gun mounts were redesigned to be interchangeable between ships. Hydraulics were simplified. Maintenance logs shortened. Each decision echoed Hyde's old philosophy: machines must serve men, not enslave them. In 1947, a small committee within the Office of Naval Research coined a new term for this doctrine: operational continuity engineering. It was a sterile phrase, but beneath it lay the spirit of the $20 weapon. The Navy's goal became to ensure that no single failure could stop a ship, a system, or a mission. This thinking soon spread beyond the sea. The Air Force adopted similar standards for its emerging jet bombers, emphasizing simplicity over luxury. Even NASA's early prototypes, decades later, would draw from this same lineage of modular reliability. Historians often focus on the spectacular inventions of the post-war years, the atomic bomb, radar, the jet engine, but hidden beneath those marvels was an invisible revolution of restraint. The men who had fought with tools that never failed understood that technology's greatest triumph was not its complexity, but its constancy. The post-war Navy, armed with this knowledge, rebuilt itself not as a fleet of machines, but as a system of trust. In the years after Japan's surrender, George Hyde faded quietly from public view. He continued working in engineering, consulting on small arms and production processes, never chasing fame. His name appeared only in footnotes, buried in reports about tooling efficiency and field repair metrics. But to those who knew, he was a legend. At an Ordnance symposium in 1948, an admiral stood before a room of young engineers and said, "Gentlemen, the next war will not be won by cost or power, it will be won by the machine that works when everything else stops." On the slide behind him was a photograph of Hyde's unassuming $20 weapon. The post-war Navy began modernizing with that creed. Carriers like the USS Midway and USS Franklin D. Roosevelt underwent extensive redesigns, their systems compartmentalized, their circuits redundant, their weapon controls simplified. The new generation of aircraft, F-9F Panthers, F-2H Banshees, and the mighty Sky Raiders, were built around ease of maintenance, quick turnaround, and modular weapons integration. Pilots, mechanics, and engineers all operated within a system of engineered trust. In 1950, when war erupted again in Korea, this doctrine was tested under fire. American carriers launched near-continuous operations off the peninsula, striking rail lines, bridges, and supply convoys. Decks battered by freezing winds and rough seas still functioned with surgical precision. Reports from Task Force 77 recorded aircraft sortie rates that would have been impossible in 1942. Machines endured weeks of salt, ice, and shrapnel without catastrophic failure. The Navy had entered a new era, the age of unbroken momentum. The Korean War was brutal and chaotic, yet amid its smoke and ruin, the legacy of Hyde's design shone like a quiet constant. Pilots trusted their equipment completely. They flew low, they fought hard, and when their guns roared, they never feared silence. Maintenance teams, guided by modular diagrams and field repair kits, restored battle-damaged systems within hours. Every link of the war machine was stronger because it had learned the gospel of simplicity. Declassified memos from the Pentagon's Naval Analysis Division reveal that post-Korea evaluations directly credited wartime reliability improvements for saving thousands of lives. One report concluded, "The continuity of strike power achieved by current carrier groups owes measurable lineage to pre-war ordnance innovations emphasizing minimal failure dependency." That bureaucratic language was a faint echo of George Hyde's genius, still rippling through time. But the legacy did not stop there. During the 1950s, as the Cold War froze the globe into tension, the Navy faced a new challenge: nuclear deterrence. Submarines, long-range bombers, and missile carriers required systems that could remain operational for months without human intervention. The lessons from a $20 weapon became the backbone of America's strategic infrastructure. Redundancy, simplicity, modularity, these were no longer technical luxuries, they were matters of survival. Every nuclear control system, every guidance array, every launch mechanism was built around the principle that failure was not an option. The same mindset that once guided a submachine gun's trigger now guided the hand of a nation staring into atomic dawn. In 1956, the Chief of Naval Operations issued a confidential directive referencing Hyde-class design requirements for all next-generation systems, ensuring that any essential control could be maintained, replaced, or bypassed by the crew at sea. Even the mighty aircraft carriers of the Forrestal class, the first of the supercarriers, bore this philosophy deep within their blueprints. George Hyde never lived to see the atomic fleet that his ideas helped inspire. He died quietly, his name fading into industrial anonymity. Yet his fingerprints were everywhere, from the smallest machine gun to the largest ship afloat. The simplicity of his vision had scaled into the architecture of global power. When the Navy historians of the 1960s looked back on the transformation of the American fleet, they noted that the carrier strike capacity of 1945 had effectively doubled again by the early Cold War, without doubling cost or manpower. They attributed it to automation, training, and resource allocation. But buried deeper in those studies was the real truth. The systems worked because they were designed to endure. They worked because a single engineer once refused to make things complicated. The Cold War generation of sailors inherited that quiet confidence. They manned radar stations and missile decks with the same certainty that their grandfathers once held a $20 gun. When storms rolled over the Pacific and the ships pitched through black water, the machines around them held steady. There was no glamour in it, no fame, just function. And that function, steady and unbroken, became the invisible armor of the United States Navy. By the early 1960s, the United States had become a technological empire. Its carriers prowled every ocean, its bombers crossed continents, and its satellites began peering into the silent dark beyond the atmosphere. Yet beneath all that spectacle, beneath the rockets, reactors, and radars, there remained a quiet current of thought born from an engineer's simple creed: reliability is strength. George Hyde's philosophy had outlived its creator, spreading like an invisible inheritance through the entire industrial soul of the nation. When President Kennedy announced America's intention to go to the moon, the challenge that followed was not just one of exploration, but of endurance. How could a machine built by human hands survive the void? How could systems remain functional through radiation, vacuum, and time? Engineers at NASA's newly formed Marshall Space Flight Center studied everything from missile gyros to Navy gun triggers, tracing back the proven principles of failure-proof design. Among the countless internal memos circulating in those years, one line from a systems engineer stands out: "Space will forgive no complexity. Simplicity is survival." It was the same truth that had saved men on carriers 2 decades earlier. At the same time, across the Pacific once again, a new war was brewing. Vietnam would test not just courage but engineering. America's vast military machine, now digital, automated, and dispersed, needed to function in heat, mud, and chaos. The lessons of the Second World War returned like old friends. In the rice fields and jungles, soldiers carried weapons descended directly from Hyde's principles: fewer parts, easier repair, faster operation. The philosophy that had made the Navy's tools unstoppable now defined American ground warfare. Meanwhile, at sea, carriers evolved yet again. The introduction of jet fighters and missile systems brought immense complexity, but the Navy remembered the past. Each new vessel was built around redundant systems, quick access panels, and compartmentalized safety. Manuals grew thinner. Crews grew more confident. The USS Enterprise, the first nuclear-powered carrier, embodied the perfection of this doctrine, capable of sailing around the world without refueling, yet so meticulously simplified in internal design that critical repairs could be made mid-ocean. In one training manual from 1965, a section was titled, "Hyde Principles Applied to Nuclear Maintenance." Few sailors understood the origin of the phrase, but the meaning was clear: keep it simple, make it last, never let it fail. Even in air combat, this thinking had taken root. The F-4 Phantom II, America's mainstay jet of the era, was infamous for its raw power but also admired for the simplicity of its maintenance. Mechanics in Southeast Asia kept them flying in monsoon rain, day after day, because the systems were built to endure punishment. Pilots joked that their jets had Navy bones, a compliment born from the same lineage of reliability that had once lived in a $20 gun. The broader American industry followed suit. Automakers, machine tool manufacturers, even consumer appliance designers began adopting Hyde-inspired production logic: fewer unique parts, modular assembly, longer service life. It was more than engineering, it was a national philosophy. America had become addicted to things that worked. The great irony was that the very simplicity born of war now powered peace, industry, and prosperity. Yet the military never forgot the origins. Within the Pentagon's design councils, officers spoke often of the old Ordnance truths. They meant the lessons of the Second World War, the time when failure meant death and reliability meant life. A 1968 lecture at the Naval Postgraduate School summarized it perfectly: the measure of engineering greatness is not in novelty, but in the number of lives a design saves by never faltering. The speaker showed a black and white photo of George Hyde's wartime prototype. For the students in that hall, many too young to remember 1945, it was a relic. But for those who understood, it was scripture. The late 1960s were a paradox. America was reaching for the moon while fighting in the jungles of Vietnam, its engineers split between the stars and the earth. Yet in both realms, the same philosophy prevailed. At Cape Kennedy, technicians tightened bolts on Saturn V rockets, each fastener tested a dozen times over. In Da Nang, Mechanics stripped down helicopter gearboxes and reassembled them by memory. Both actions were born of the same belief: precision means nothing if it cannot endure. When Neil Armstrong took his first steps on the lunar surface in 1969, the world heard his words, but the engineers heard something else: the sound of systems working flawlessly after years of design, testing, and faith in simplicity. In mission debriefings, NASA credited modularity and fault tolerance as keys to success. Those were Hyde's values in cosmic form. What had once made an aircraft carrier strike twice as hard now had sent a man to the moon and brought him home alive. Back on Earth, the Navy continued to evolve. By the 1970s, it was no longer a fleet of ships alone, but a networked organism of computers, satellites, and electronic warfare systems. Yet the core remained unchanged. Nothing complicated for the sake of complexity. Every circuit, every relay, every piece of software had to survive the ocean, the salt, the shock, and the unknown. One admiral, when inspecting a new carrier's control room, asked a young technician how many redundant backups were installed. 3, sir, he answered. Good, said the admiral, then she's built like Hyde would have wanted. Even as technology advanced, the engineers never escaped the shadow of that lesson. In times of peace, it guided restraint. In times of war, it guaranteed victory. The $20 gun had long vanished from armories, replaced by modern rifles and automated defenses. But the soul of its design lived on in every fail-safe valve, every reinforced switch, every emergency bypass. To this day, the spirit of its creator whispered through every blueprint: don't overthink, make it work. As the Cold War deepened, this principle became America's quiet weapon. While adversaries built machines of terrifying complexity, the United States focused on systems that could be repaired in the field, operated by tired hands, and trusted under pressure. The Navy's carriers became not just symbols of power, but embodiments of endurance. They could launch missions around the clock, survive damage, and fight on, just as their World War II ancestors had, only now with the precision of computers and the strength of nuclear power. Behind every system's reliability was a legacy traced to one engineer who never sought glory. George Hyde's story was not one of heroism, but of purpose. He never commanded ships or designed rockets. He simply asked what would happen if every part of a machine refused to fail. In answering that question, he changed the very language of engineering. The 1970s passed, and with them the veterans of his era grew old. Many never knew his name, but they knew the feeling of trust. The quiet certainty when a trigger pulled, a switch flipped, or a turbine roared to life. That was his monument. Invisible, practical, eternal. And though the world changed, though computers replaced steel and code replaced gears, the principle stayed. Reliability remained the invisible force behind progress, the bridge between chaos and control. It was the one lesson America carried from the war into every generation after. Build it simple, build it strong, and it will never fail you. By the dawn of the 1980s, the world had entered an age where power was measured not only in weapons but in endurance. The Cold War had matured into a silent competition of reliability, which nation systems could last longer, react faster, fail less. And as America's supercarriers cut through the oceans, each bearing the weight of nuclear capability and decades of accumulated doctrine, one truth stood unshaken: simplicity still ruled the seas. The USS Nimitz, launched in 1975, embodied the summit of that philosophy. Beneath her decks stretched an empire of machinery: turbines, launch catapults, nuclear reactors, and radar networks, all bound together not by elegance but by function. Her engineers often remarked that the ship felt almost alive, a self-healing organism built to keep fighting no matter what broke. This was Hyde's dream evolved to perfection. A single engineer's $20 vision had multiplied across generations until it now commanded entire oceans. Inside the ship's control rooms, computers hummed, yet their architecture followed the same lineage of thought that once guided the $20 weapon. Everything could be bypassed, replaced, or repaired at sea. Each system was redundant, its twin already waiting in silence should the first one fail. Sailors were trained not just to operate machinery but to understand it intimately, to trust that nothing aboard their steel world was too complex to master. That was the essence of the Hyde standard made manifest in steel, wire, and willpower. Naval training manuals of the 1980s carried phrases that echoed directly from his philosophy: redundancy is survival. Simplicity under pressure. Failure exists only once. These weren't slogans. They were mantras drilled into generations of sailors who understood that perfection at sea was not about glamour but about persistence. By now, the philosophy had spread far beyond the Navy. The Army's missile defense networks, the Air Force's strategic bombers, NASA's space shuttles, all shared the same DNA of reliable design. When the Space Shuttle Columbia first lifted off in 1981, its systems were a testament to the Navy's enduring lessons. Thousands of circuits, relays, and control pathways had been tested to failure and rebuilt to resist it. Engineers who had grown up reading about the Pacific War now designed machines for the heavens, guided by the same truth: what works on the ocean must work in the void. The Space Shuttle program, with its reusable design, was perhaps the ultimate reflection of the Hyde principle. Its brilliance lay not in newness but in repeatability. Each mission demanded perfection through familiarity, components reused, repaired, and trusted again. It was the mechanical embodiment of reliability, a child of the same American spirit that once built a $20 weapon to never fail. Meanwhile, deep beneath the seas, submarines like the Ohio class carried nuclear missiles, maintaining their silent vigil for months without surfacing. Their systems, too, owed their resilience to that same lineage of design restraint. Engineers who maintained them used to say, "If it breaks, we can fix it underwater." That was no boast. It was a philosophy handed down through generations of American builders who had learned that the ultimate power is endurance. Throughout the late 20th century, as computers invaded every facet of life, a quiet battle raged between complexity and reliability. Software engineers began quoting old Navy doctrines. Redundant backups, modularity, fail-safe protocols, all concepts that first appeared on wartime blueprints now lived in lines of digital code. The architecture of the modern world, from air traffic systems to nuclear control grids, was built on that same timeless foundation. Don't let it fail. Even in moments of tragedy, the lesson endured. When Challenger was lost in 1986, the nation mourned, but engineers didn't turn away from simplicity. Instead, they returned to Hyde's philosophy, studying what could be made more reliable, what systems could be made less fragile. From the ruins of failure, America once again rebuilt around resilience. Every generation rediscovered the same truth: complexity can dazzle, but simplicity endures. By the 1990s, the doctrine of reliability had become so deeply embedded in American identity that it transcended technology. It became cultural. From factories to battlefields to corporate offices, the idea of building things that just work became synonymous with American craftsmanship. The Navy codified the principle officially in its 1991 Systems Maintenance Directive, which stated, "The reliability of function defines the reliability of force." Hidden deep in the appendix was a historical note, a single reference to George Hyde's wartime weapon, still cited as the earliest example of modular functional continuity in combat arms. That small footnote was the last time the U.S. government officially mentioned his name. Yet his invisible presence lingered in every field that demanded absolute trust. Civil aviation, medical devices, space exploration, all bore the fingerprints of a man who once asked only that his weapon never fail. As the 21st century dawned, his legacy quietly evolved into a global standard. Engineers across the world, in Tokyo, Berlin, Tel Aviv, and Cape Canaveral, taught his principles under new names: fault tolerance, robustness, design for maintainability. Few remembered the humble gun that started it, but all inherited its wisdom. The idea had become universal, a law of engineering itself. Back in the United States, the Navy prepared for a new generation of carriers, the Nimitz-class successors, culminating in the USS Gerald R. Ford, a marvel of digital and mechanical reliability. It launched aircraft with electromagnetic precision, powered by twin reactors that could run for decades without refueling. And yet, despite all the futuristic systems, the engineers who built her still spoke of simplicity. In her design documents, a guiding principle appeared again, unchanged after nearly a century: design must ensure total operational continuity under duress. That was Hyde's voice, echoing across time. From the $20 gun built in a small wartime workshop to a 100,000-ton nuclear carrier dominating the seas, the distance was vast, yet the philosophy was identical. Reliability had become not just a military necessity but a moral one, the belief that no life should be lost to preventable failure, no mission compromised by fragile design. To many, That belief became the silent religion of American engineers, faith in the machine that endures. They didn't build monuments to Hyde, but they built his ideals into every engine, circuit, and bridge. At the turn of the millennium, when the Navy declassified much of its World War II ordnance history, a handful of researchers stumbled upon the original wartime memos referencing the Hyde prototype. They marveled at its simplicity, its cost, its raw genius. And in those faded diagrams, one could almost see the seed of an empire, a sketch that became a standard, a weapon that became a world philosophy. History had moved on. The names of admirals and presidents filled textbooks, but the engineer's name rarely appeared. Yet his impact remained deeper than glory could measure. Nations rise on invention, but they survive on reliability, and Hyde's invention had given America both. As the new century unfolded, his legacy found strange echoes in places he could never have imagined. In Mars rovers built to survive years of dust storms, in autonomous drones designed to operate with no human hand, in data centers that power civilization itself. Every time an American engineer designed something that just worked, Hyde's ghost nodded in quiet approval. He had not merely built a gun. He had built a principle. And that principle, that perfection is not found in what is added, but in what never fails, would outlive empires, wars, and even the machines themselves. In the end, when historians look back at the great sweep of the 20th century, the wars, the triumphs, the rockets, the oceans, they find that the story of progress is rarely written by those who commanded armies or held nations in their hands. It is written by the quiet ones, the men and women who built things that worked. Among them, one engineer stands as a symbol of everything America became in its hour of need: George Hyde. He never led a battalion, never addressed a crowd, and never asked for applause. His hands shaped steel, his mind shaped endurance, and his invention, a gun that cost less than a pair of boots, helped turn the tide of a global war. His weapon did not dazzle, it simply refused to fail. And in that refusal, it taught a nation what true strength meant. When the war ended, the world celebrated the mighty, the bombers, the generals, the cities rebuilt. But beneath the noise, Hyde's lesson endured in the hearts of those who understood the real miracle, that greatness lies in the ordinary working flawlessly. The $20 gun had become more than a tool of war. It was a quiet promise between engineer and soldier: I will not let you down. Decades passed and the machines changed. Steel gave way to silicon, gears to code, and pilots to algorithms. But Hyde's invisible signature lingered everywhere. In the hum of engines, in the precision of flight decks, in the calm confidence of sailors who trusted their machines as they once trusted each other. The Navy that once struggled to keep its aircraft armed now commands the oceans with systems that run for years without rest. And somewhere in that endless rhythm, the hiss of turbines, the click of relays, the pulse of radar, lives the echo of an idea born in a simple workshop. Every great nation is built not by what it dreams, but by what it keeps working. Hyde's weapon worked. And that reliability became America's language, the grammar of victory, the heartbeat of progress, the unseen thread that connected 1942 to the modern age. His legacy was not one of destruction, but of precision and faith, the faith that human hands could create something worthy of absolute trust. If you look closely at the photographs of the Pacific Fleet, the ones showing sailors on the deck, planes poised for takeoff, waves crashing against steel, you will see it. Not the glory, not the fire, but the quiet, the calm, the confidence. That is the legacy of George Hyde. His $20 idea became a million acts of certainty. His simplicity became the architecture of survival. His reliability became the rhythm of freedom itself. History will always remember the weapons that roared, but it should never forget the one that simply worked. Because in that simple, unbreakable, enduring machine, forged not from pride but from purpose, lived the spirit of a nation that believed in function before fame. And through that belief it conquered chaos. So as long as there are engineers who dream of reliability, sailors who trust their tools, and people who still believe that greatness begins with something that just works, the spirit of George Hyde will never die. His story reminds us that history's loudest victories are often built by the quietest hands. If you honor history, subscribe, leave a like, and share your thoughts in the comments.